without any further ado, please welcome Jeremy Evans.
Great. Thank you very much. Thanks for having me here this morning. I bet you can hardly wait to get out of here. Okay, this is going to be a complete change of pace. I mean, we started with David, who's young and handsome, very dynamic, and obviously very, very clever. And now you're stuck with me, who's old. My wife tells me whatever good looks I had are long gone. I've been called stoic, among a lot of other things, and a whiteboard and 2 flip charts as far as my prompts. So what we're going to do now is, first of all, get out your calculators. We're going to have you do the calculations. So if you brought your calculator, get it out, get it fired up. I need at least 3 because I don't trust the first answer I always get. And we're going to do a quick review of some of the things David did just to make sure we drive them home. And I think this is probably the most important chart he had. By the way, if you want copies of the charts, one of the gentlemen came up and photographed them, and he's going to put them online or make them available. You can email him, bobmac3@aol.com, and he'll be happy to send you a copy of David's slides, assuming that David thinks that's okay. And I can pick on him because he's still in the back of the room. Okay. And everybody got a handout from the front when they came in, the presentation material. I apologize a little bit. I didn't make a cover based on the CLSA conference. This is one I did for San Bernardino Riverside chapter a few years ago, and I'm just going to use the same problem. We're also going to be working down in Zone 6 as opposed to Zone 3 or whatever would be up here. Also, is there anybody here from Nevada? Okay, this isn't going to work real well for you guys because California is Lambert, Nevada is Transverse Mercator. I think the angle and the distance calcs will be the same, but the coordinate calcs will be completely different. But anyway, we'll go through it and see what happens. Okay, let's do a quick review then. I'm going to start with a little bit of a simple concept here, and I hope you all can see this as we go through. And we go like this, something like this, and we call this A and B, and we'll call this, did that wrong, oh well, A prime and B prime. And work from there. Okay, if we have concentric circles, okay, and we have A to B along here, A prime to B prime along here, which is going to be the shorter distance, A to B or A prime B prime? A prime B prime, right? Okay, and if I were to draw a chord, I shouldn't have done this one, draw a chord through A prime B prime, what's going to be shorter, the chord A prime B prime or the arc A prime B prime? The chord, right? Okay, you now know 90% of what you need to know about state plane coordinates. And we're going to spend the next 2.5 hours talking about the other 10% that you need to know to finish up, okay? And this relates back to David Johnson's sketch here. A to B is the Earth's surface. Okay? 2 things about the Earth's surface that are important. What are they? And I ask a lot of questions. It's curved. That's not one of them. Gravity. Okay, first of all, it's where we work. Okay? And secondly, it's the only real surface we're going to talk about. Every other surface we talk about is fictional or theoretical or whatever you want to call it. So this is what's important here. This is where we work, and this is the only real surface. Everything else we deal with is mathematical or fictional type of concept. All of these other surfaces, the ellipsoid, the geoid, the grid plane that we'll work on in a minute, are all tied together very well mathematically. The hard part is getting from the Earth's surface to those mathematics. That's where we get our error sources in state plane coordinates. By the way, why do we have state plane coordinates? Besides to torture you on the LS exam. Anybody know when the state plane coordinate system was created? When? 1935. 1935 in North Carolina was the first state plane coordinate system. If you were a surveyor in 1935, did you have an HP 48? Probably had a slide rule, right? Geodetic computations are very, very hard. Not as hard nowadays because we have computers and everything, but back in the day, geodetic calculations, spherical geometry, was pretty hard to do on a slide rule and things. So they developed this state plane, PLANE, coordinate system where we could do geodetic surveying, geodetic quality surveying on a plane, PLANE surface, and use plane trigonometry to do our calculations. It's been around for a long time. I would estimate that probably in the next 10 years or so, state plane coordinates will be gone. That'll be a good thing. No more of that in the exam. The bad thing is you'll be expected to do spherical trigonometry and do geodetic calculations. That's the bad thing. There's really no reason for us to have state plane coordinates anymore other than legacy data. That's the only reason we're using it anymore. Okay, anyway, moving on from there. Now I completely forgot where I was. Okay, so we have our surface, we have the geoid. 2 words define the geoid. The simplest 2 words you can come up with for the geoid. Sea level. The geoid is sea level. Okay, those are the 2 simplest words. If you let the oceans come to rest, take the current out, take the tide out, get rid of all that stuff, and the ocean comes to rest, that's the geoid. And as David mentioned, because of gravitational effects, it's going to be this lumpy surface that's non-mathematical. Okay, so we created the ellipsoids or the datums that are a mathematical representation of sea level. We create the ellipsoid, the datum. Anybody know the difference between the ellipsoid and the datum? We use them kind of simultaneously or whatever that magic word is. Anybody know the difference?
An ellipsoid is just an object. Once you fix it, it's a datum.
Exactly. The ellipsoid is simply the spheroid or the ellipsoid. It's the object. It's the shape. That's GRS 80. Once you tie it to whatever it is you're tying it to, then it becomes a datum. And you have to make it a datum, you have to have an orientation point and a reference direction. What's the orientation point for our datum, NAD 83? That's the ellipsoid that NAD 83 is created from, but what's the point of orientation? No, what's the point of reference? Earth mass center. What's orientation? X-axis out through the prime meridian, the y-axis 90 degrees to that, the z-axis on the spin. The z-axis is the spin axis. That makes sense? Okay, go back to 27 for a minute. Okay, what was the ellipsoid? Or what was the ellipsoid? Spheroid, Clark of 1866, which is the foundation for NAD, North American Datum of 1927, right? What's the point of origin? Meads Ranch in Kansas. It's a physical monument out in a cornfield in the middle of Kansas. Okay, you can walk to it. You can see it, you can touch it. Why did they choose Meads Ranch in the middle of Kansas?
Geometric center.
Geographic center of North America. Okay, because NAD 27 was for North America only. They're not using it in Europe, they're not using it in Australia, they used it in North America. Okay, what was the orientation? One of the azimuth marks to Meads Ranch was the orientation. Azimuth mark 1 or 3, I can't remember what it was, but there was an azimuth mark out there that they used for orientation. Those are the difference. Local datum, NAD 27, global datum, NAD 83. Okay, that covers a real quick review of what David went through. Now, we're going to go from our geodetic surface, the datum, our geodetic coordinates, latitude and longitude, and we need to be able to do 4 things on the LS exam. You've got to go from geodetic coordinates to state plane coordinates, and vice versa. State plane coordinates back to geodetic coordinates. Okay? You need to be able to calculate a grid azimuth, and you need to be able to calculate a grid distance. You have to have grid coordinates with a grid azimuth, with a grid distance, then you get your HP out, you use your survey pack, and you simply traverse. Everything's on the same common datum. Boy, it's dry up here. I'm going to have to do this a lot. Being from the coast, I'm not used to this. Okay, questions on that? We've got to get everything through the same data. Excuse me. The state plane coordinate grid plane for this to work. Questions so far? Okay, this is going to go fast then. By the way, get your calculators out and fire them up because you're doing all the math, I think, as I mentioned. In your handout, I think I gave you a problem. Bernardino to Riverside. I hope. Looks something like this. And what I like to do is kind of teach from a problem, and we'll go through it piece by piece. Is the problem in there? Yeah, that's it. Go back. Yeah, that's it. So kind of read through the problem just like you would if you're taking the LS exam, one of the old written LS exams, not the new, whatever you want to call it, LS exams. You guys are all the guinea pigs for in California. Good luck to you. People in my class are all excited because they think the LS exam is going to be easy because it's all multiple choice like the national exam. That's not what I'm hearing. Okay, so what we're going to do in this problem is we're going to basically determine the state plane coordinates of Riverside, right? Based on the information provided. I've given you a latitude and a longitude for Bernardino, and an elevation and a geoid height, and then some constraints for zone 5 in this case. We're going to work in zone 5, not zone 6. I apologize for that. Okay, so far? Everybody understand the questions? Any questions? Okay, so let's get started and let's get into calculating what we're going to do up here, and I'll do the best I can to stay out of everybody's way. It's going to be hard. We'll do our calculations on the whiteboard. We'll keep our answers and things like that on the middle board. And then as I got to draw sketches or whatever, I'll move over to David's board over here, and we'll work our way through our sketches, okay? And see what we can do on that. So the first thing we have to do is we have to calculate, well, actually what we need to do first is how do we get to this grid plane? Okay, how do we generate this? David talked about the Earth, okay? But think of this as your ellipsoid, the ping pong ball. Transverse Mercator, for those of you in Transverse Mercator, for those of you in Nevada. And the Lambert conic conformal projection, for those of us in California, okay? So, we have our datum, and the way we go from a datum to our grid plane is through a projection. And in California, it's the Lambert. That's the guy. Conic. That's the cone. Okay. Conformal. Whenever you go from a spherical to a flat plane, what happens?
Distortion.
There's going to be distortion. You can't go from a sphere to a flat plane without some kind of distortion. You either have to, you can hold the distances and everything else goes, you can hold the areas and other things fall apart, or you can hold the angles. And what we do with the conformal is we hold the angles. And we let areas and things like that change. Now we're dealing with very small areas. We're not dealing with the whole Earth's surface. We're dealing with very small strips of land. So it's not a huge change, but there is changes. And of course, Lambert conic conformal projection. The projection is what's called and I'll do the best I can here, a developable surface. A developable surface. So, we have our lines of latitude and longitude. Are the spheres still out there, the globes, or did David take those with him? Okay. We have our lines of latitude and longitude. And somewhere on here, on our sphere, we have a point. Let's put it over here in California. And we have a point over here. Think of this in 3D. We have our point over here. We'll put it over here in California, and we have point P. Okay? And point P, I didn't get that up high enough, did I? There's the equator. Point P, if I draw this on here, point P will have a latitude. Okay? And point P also has a longitude, something like that. Agreed? That's generally what we've given. I've given that to you in the problem. Okay, so a latitude and a longitude, and it's right here on the sphere, which you can't see. Then what you do is you take this cone, still shaking a little bit, and we take this cone, put it over the ellipsoid. The axis of the cone is coincident with the axis of the ellipsoid. That makes sense? The axis of the cone is coincident with the axis of the datum. Okay, so far? Now, what's wrong if I put this over like this? What's wrong with this model right here? Pardon me? It is distorted, that's fine, but there's something else that's wrong with the whole system here.
It's not secant to the surface.
Okay, if I put the cone on here, excellent. This is a tangent surface. This cone is tangent to the edge of the ellipsoid, correct? That's not the way it works. What we do in state plane coordinates is our cone is what's called secant to the surface. Again, here's our datum, here's point P, and what will happen is the cone actually intersects and goes through the datum, something like that. It's secant to the datum, not tangent. So this is not technically correct. This is not drawn correctly, but the limits of a zone would extend from here to here. I think David mentioned it's about 156 miles. The limit of a zone in California is about 156 miles. Why isn't it exactly 156 miles?
County lines.
Yeah, we follow county lines instead of specific lines of latitude and longitude. By the way, I apologize. One of the things I didn't do was did you bring your projection table? I need to borrow that in a second. So we have the lines of longitude, or where it intersects. The zone is about 156 miles. Where this intersects here, and where it intersects here, this is about 2/3 of the zone, about 100 miles. And 1/6 and 1/6 are outside where it intersects. Clear as mud, right? Okay, so anyway, we have point P. It has a latitude. It has a longitude. We've set this cone into place. And now what we're basically going to do is project our lines of latitude, our lines of longitude from the datum to the cone. We're going to project our lines of longitude and our lines of latitude from the datum onto the cone. Does that make sense? Basically, it's projected radially for our discussion up here. So, we take our, and again, I'm not doing this real well. By the way, one thing to do, when you get back to home or you go to work tomorrow, go to your computer, go to Google, and Google Caltrans Office of Land Surveys. Caltrans Office of Land Surveys, and go down near the bottom of the page and they'll have the LSIT review material. Go to State Plane Coordinates. There is an excellent presentation by Vincent Seck in here that he goes through the whole thing in really, really fine detail, and that's a great reference. Print that out, punch it, and put it into your notebook for the LS exam. That's an excellent presentation. Anyway, we get our lines of longitude that are on the surface. We project those onto this cone. Okay? We also take our lines of longitude and do the same thing, and we project all of those onto this cone. Follow what I'm doing so far? Then what I'm going to do is we're going to develop the surface. We're simply going to cut this cone along one line. We're going to cut it, and then we're going to take it and lay it out flat. So now we take this cone, we cut it, and we're going to lay it out flat. And what's it going to look like? It's going to do something like this, right? Here's going to be the apex of the cone. We sliced up two. It's going to go like this, and then it's going to go like that, right? When we lay it out flat, it's going to end up being something like this. What's going to happen to our lines of longitude? How are they going to look on this surface? They're going to radiate out or converge on the point that was the apex of the cone, correct? So our lines of longitude are going to look something like this. Okay? Okay. What's going to happen? What's going to happen to our lines of latitude? They're going to end up being curved, right? They're going to go something. Actually, what they're going to be as at each intersection with a line of longitude, they're going to be 90 degrees, right? So they're going to end up being curved. And somewhere on here is going to be point P. Okay so far? We've projected onto the developable surface, we've sliced that surface open, and now we've laid it out onto a 2D, onto a flat surface. Now what we do is we take one of these lines of longitude and we make it the basis of our plane, P-L-A-N-E, coordinate system. And that line is central meridian. It's the central meridian of the zone, is the chosen line. And we take that line. That's not a good choice, is it? And we take that line. That's not a good choice either, but I don't have any other choices. And our grid system, our state plane coordinate grid system, is parallel and perpendicular to that central meridian. So now we have a grid system that goes like this, is parallel and perpendicular to the central meridian, and now point P has a northing and an easting also. Does that make sense? Okay, so what I've graphically showed you is how the state plane coordinate system works. And what we're going to do now is spend the rest of our time mathematically doing the same thing. And then we'll work with 2 points and how do we traverse between them. Questions? Okay. Okay, so let's go another step. And the way we do this, to do the calculation mathematically, okay, so we have let's just work through our problem. Let's do it this way. And we're going to start with point Bernardino. Okay, first of all, is Bernardino, and this is zone 5, so you need to know the constants for zone 5, which you have there. Is Bernardino east or west of the central meridian? Remember, this is a review, so I get to ask the questions. Is Bernardino east or west of the central meridian? How do you know? Pardon me? No, it has nothing to do with the mountain. This has to do with the San Bernardino Riverside chapter of CLSA. Look at the geodetic longitude. Okay, what is the longitude of Bernardino? 116.54, blah, 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 right? What is the longitude of the central meridian? 118. Therefore, it's going to be, well, wait a minute, it's a smaller number. Shouldn't it be west? We're measuring west longitude. Therefore, longitude increases going east, right? I see some confused looks. Longitude increases to the east. No, longitude increases to the west. I know there's some confused looks because I'm confused. Longitude increases to the west. Therefore, if central meridian's at 118, longitude is 116, it's going to be east of the central meridian, correct? So I have to put the central meridian here, and Bernardino is going to be over here, correct? It's east of, so it's Bernardino is over here. Everybody okay so far? Now, based on the central meridian, which is L sub O, if you go to the end of your handouts, there's a whole bunch of constants for the zones, a lot of L sub O's and B sub O's and L sub this and B sub that. Those are the abbreviations for all these different things. The abbreviation for the central parallel is L sub O. And that's how I'll try to remember to show it. So L sub O is the abbreviation for the central meridian. And what we create here, based on this, is what's called the Lambert triangle. Apex of the cone. This line is obviously, this is the apex of the cone. Here's Point Bernardino, and Bernardino has a longitude, right? Longitude is based on from the apex of the cone through the point, and Bernardino also has a latitude. Okay so far? Okay. Somewhere way over here to the west is the origin of the zone, and it has a coordinate, true origin of the zone, and it has a coordinate of north 0 and a coordinate of east 0. Everybody would agree with that? If we're dealing with coordinates, northings and eastings, somewhere there's an E0 and a 0. Okay. Anybody know what this is called? This would be, what would this line represent in coordinates? Think of northings and eastings. This dimension right here, from here to here, would represent the easting of the central meridian, right? Would represent the easting of the central meridian. E sub 0? E sub O, not E sub 0. E sub O. And E sub O for zone 5 is what? It's on the front page. You're way too fast for me. 6, 5, 6. Thanks. The value of E sub 0, the easting of the central meridian, is 6,561,666.667. Everybody find that for the constants of the zone? As a matter of fact, E sub O is the same for every zone. And there's a real easy way to remember it. E sub O is the same for every zone, and there's a very easy way to remember what the value is. What's this value in meters? 2 million. The E sub O of every zone in California is 2 million meters. And how do you convert from meters to feet? Thank you. 39.37. What is that value?
Number of inches in a meter.
It's the number of inches in a meter. Using which, is that a U.S. survey foot or international foot? That's U.S. survey foot. Everybody know the difference? There's 39.37 inches in a meter, exactly, U.S. survey foot. There's 2.54 centimeters per inch, exactly, in an international foot. The difference is about 100th in a mile. 2 parts per million. Why do we care between the difference? Because when you get out to 6 million feet, it's about 13 feet of difference. Okay? I had a party chief call one morning. It was a state plane coordinate job, a pipeline project, and he was missing the check-in point by 13 feet. I said, check your data collector. Are you on international feed or are you on U.S. survey feed? He was on international feed. Is Nevada U.S. survey foot? Yeah, Arizona is international foot. Okay, Arizona is an international foot state. Why did we stay on U.S. survey feed in California and Nevada? Because all our old records are U.S. survey feed. Okay, let's keep going. Okay, so we have this value here. Along the central meridian here, we have a point here that's called the point of origin. Yeah, point of origin. What's the northing of that point? Kind of a false origin, if you will. The real origin's down here. The point of origin for the zone's up a little bit. Real easy one to remember also. What's the value of that from here up to the point of origin? 2 million meters. And that value is called N sub B. It's a constant for every zone. This value right here is N sub B. The distance from zero northing up to the point of origin is called N sub B. The easy way to remember it is it's 2 million meters, which equals, in feet, 1 million. It's in the handout. Sorry, I can only do one person. Is this right? No, it's 500,000 meters, sorry. Yeah, it's 500,000 meters. 2 million meters, 500,000 meters. I'm confusing myself. 2 million meters, 500,000 meters. And they're the same for both zones. I'm sorry. So N sub B is 2 million meters. The origin of the zone, the northing of the easting of the origin of the zone is 5 million north, 500,000 north, 2 million east, which we've simply converted to feet. Okay, 3 other constants. Actually, we have one. L sub O is a constant for the zone. It's 118 degrees, 00 minutes west longitude. Another constant for the zone. The distance from the point of origin to the apex of the zone is a constant. Okay, and it's called R sub B. It's a radius value. It's called R sub B. Let's write down the value first. And it's a big number, like 32 million something. Yeah. R sub B.
306,487,44.932.
I got confused after the first 7. 6487.
306,487,44.
Wait a minute. Now you've got me totally confused. Okay, I've got 30,648,744. 744. Does everybody find R sub B? Okay, a constant for the zone. This changes in each zone. Okay, and that makes sense.
That's from where to where again?
That is the distance from the point of origin, the false origin, or whatever you want to call it, point of origin, to the apex of the cone. Okay? And if you look at this, if this is California down here, this cone's going to be longer. As you move north through the state, the cone's going to end up being flatter. It's longer. As you move north through the state, it's going to end up being flatter. So R sub B changes for every zone. It's a constant for each zone, but it changes. 6 to 5 to 4, this number decreases. Okay, so far? 1, 2, 3, 4. We have one more constant for the zone. It's the sine of B sub 0.
Ready?
Yep, 0.
0.570011899611. 5174.
5720 1189 6174. Okay, we'll come back to this one. We'll come back to this one in a minute. Okay, so those are the constants for the zone. Oop. And we have point B here. We have R sub B. So, if we look at our Lambert triangle here, I think in Lambert triangle this is gamma, and that's what this is supposed to represent. I know I'm not doing my Greek letter perfectly, but this is gamma. Gamma used to be known as the mapping angle. It's now known in NAD 83 as the convergence angle. Gamma is the convergence angle. In 27, it used to be called the mapping angle. The dimension from the dimension from the apex of the cone to our point is known as R. The dimension from the apex of the cone to our point is known as R. And this is a right triangle. Based on this, and without looking at your handouts, how do we calculate the northing of B? Based on the information we have here, how would we calculate the northing of B? Maybe there's one more step we need to look at. What's the value of this side of the triangle? It would be R cosine gamma, right? Adjacent over hypotenuse, cosine value. And if this is R cosine gamma, this must be R sine gamma. I apologize. I asked for a big whiteboard, but this is what we get. Now, based on the information provided and without looking at your sheet, how do you determine the northing of point B? Just give me a formula. You have all the information you need to give me a formula for the northing of point B. Okay. The northing of point B is going to equal R sub B plus N sub B. Stop there. What's that value? R sub B plus N sub B gives me what? The northing of the apex of the cone, right? N sub B plus R sub B gives me the northing of the apex of the cone, correct? If I subtract R cosine gamma from that, if I subtract this from this, I'm going to have, if I extend this out and do it, this value here is going to be my northing, correct? Questions? Okay, what's going to be the easting of point B? What's going to be the easting of point B? It's going to be E sub O, right? Plus R sine gamma. So the easting is going to equal E sub O plus R sine gamma. Now, if our point was west of the central meridian, then it would be E sub O minus R sine gamma, right? Wrong. It's still E sub O plus R sine gamma. Anybody know why?
Negative.
Gamma is always negative west of the central meridian. Gamma will always be negative west of the central meridian. If you can draw this sketch, hopefully a lot neater than this, but if you can draw the Lambert triangle and understand how the constants fit and how these values fit in, you don't have to memorize any formulas. The only thing you have to remember is gamma is positive east and negative west of the central meridian. Then it's just trigonometry. Okay, so based on these two formulas here, we've got to figure out what R is, and we've got to figure out what gamma is. Okay? Let's do R first. Okay, and this is where it gets a little bit tricky, and I'm going to borrow. For the LS exam, there's two ways to calculate R. You can calculate R using the projection tables. And for the LS exam and using your handheld calculator, this is the way I recommend to do it. And this is how we're going to do it in class. Okay? Because they've already generated the R value for every even minute of latitude. So they've done a lot of the calculations for you, and all we're going to do is proportion between. You can also do it by what's called polynomial coefficients. In polynomial coefficients, they give you the value of R for the central parallel only. And then you calculate where B is based on the central parallel of the zone. The problem there is you're going hundreds of thousands of feet potentially, and you can't do a simple proportion. It's a very intensive math. The formulas are relatively easy. They're just a lot to them and a lot of chances for mistakes. A lot easier with your calculator to do this. If you're going to program your calculator, if you're that smart, then you're going to use polynomial coefficients. If you're going to do it by hand, I would recommend highly that you use the projection tables. CLSA sells them. Unfortunately, they've already packed them away, so you're going to have to order them through the mail. I tried to get my copy this morning since I forgot mine from home.
How many exams do they give you the table?
No. They'll give you the polynomial coefficients. So bring the projection tables with you. I asked Rick Moore when he was the head of the LS. He was the LS, whatever you call him. I called him once and I said, if the LS problem gives you all the polynomial coefficients, do you have to solve it that way? And he said, no. You can solve it using projection tables and you should get full credit. Because they give you, surprisingly enough, the same answer. Okay? It's just easier using the projection tables. Okay, so based on that, and somewhere in your handouts, I've given you the page of the projection tables you need for this problem. Okay? And let me borrow yours for a second. It's this one right here. Oop, right there. And it looks like this. It's got Zone 5, California mapping radius, North American datum, 1983 at the top. And about 5 columns, no, more than that. 6 columns across. And if you look at the 1, 2, 3, 4th column, you're going to see R, U.S. survey foot. If you go to the 4th column, you're going to see R in U.S. survey feet. Everybody see that? And they've given you this value of R for every even minute of latitude. They've given you the value of R for every even minute of latitude. So all we're going to do is we're just going to simply proportion between to come up with our value for B. Now, there's also a column here, the next to last column over, called the tabular difference. Tabular difference. Everybody see it? Okay, somebody with your calculator. What's the circumference? I want you to do the calculation for me. What's the circumference of the Earth in miles? Anybody know? It's about 25,000 miles. So if you got a calculator, punch in 25,000. Okay? Multiply that by 5,280. Now, don't give me the number, but what does that value represent? The circumference of the Earth in feet, correct? Okay, so far? Divide that by 60. Excuse me, I'm sorry, divide that by 360. What would that represent? the length of 1 degree of latitude. No, yeah, latitude, or we're talking about at the equator. So 1 degree of longitude. We're going to deal in latitude. Everybody follow what I'm saying? Divide that by 60. That would represent 1 minute, correct? Divide by 60. That's going to represent the length in linear feet of 1 second, right? 1 second of the circumference of the Earth, correct? And what's that number? 101.8 something, correct? What's the numbers over here in the next to last column? 101 point, in this case, but it's still around 101 feet. The tabular difference is simply the distance in feet for every 1 second of longitude. The tabular difference, and it's between each even minute. The tabular difference is the distance in feet for every 1 second of longitude. So they're letting us they're doing kind of the proportion for you here. So, now I'm lost. I'm running out of space. I'm going to go to here. Okay, the longitude of point B is what? Excuse me, I need the latitude. I'm sorry, I'm really bad today. B sub B. Latitude is always given by B. That's the symbol. I apologize. What's the latitude of Bernardino? 40.
42.54378.
Okay, seconds. And why do we carry it out to five decimal places? Because that's about equivalent to 1/100th of a foot. 5 decimal places in a latitude or a longitude is equal to approximately 1/100th of a foot. Actually, a little bit tighter than that. Okay, so 3417 is here. So let's draw in the 34 degree 17-minute line of latitude. Is the 34 degree 17-minute line of latitude going to be below or above B? Is it going to be down here? Or do I draw it down here or do I draw it up here? Latitude increases to the north, right? So I'm going to draw it in down here. 34 degrees, 17 minutes. Okay, so gotten to there. Okay, and what's the R value from your projection tables for 34 degrees, 17 minutes? Don't all shout it out at once.
33,669,115.
Does everybody see that in the projection tables? I'm going to steal yours again. I apologize. Go to 34 degrees and make sure when you're using the projection table, make sure you're doing the correct degrees here at the top. They go from about 32 to 34, so it's easy to get on the wrong page. Make sure it's 34 at the top. Find 17, which is 3 up from the bottom. Go over to the U.S. survey foot. Don't use meters. Go over to U.S. survey foot, and it's 33,336,669,115. We got it right. Okay, so that's the distance to here. So we know, and this is getting to be a mess. I apologize. This is R for 34 degrees, 17 minutes, clear down to here. Everybody okay so far? I got to convert this to a PowerPoint one of these days. Okay, now how are we going to calculate, if we can calculate this distance here and do a subtraction, we can then get R for Point Bernardino. So how are we going to do that? Well, we know the number of seconds. So all we have to do is take the number of seconds times the distance in linear feet per second and do a multiplication, right? So if we multiply 42.547378 times 101 point what?
08843.
It's going to be between 17 minutes and 18 minutes. So it's going to be 101.08846. Everybody see that? The tab difference between 3417 and 3418 is going to be 101.08846. Yes? So, if you multiply this times this, you're going to get what? Somebody's got a calculator and they're afraid to use it. Okay, well, I got 4,300.685 feet. Are we okay so far? And this represents, I call this dimension right here, I just call it the difference in R, delta R. So the value of R for Point Bernardino is going to equal what? It's going to be the R value for 3417 minus our difference in R, right? I've got a lot of confused faces out here. I told you it'd be about as clear as mud. What am I saying wrong besides all the mistakes I'm making that's confusing you? Okay, now do I subtract this from this or do I add it? I'm going to have to subtract it, aren't I? I know the value here. I want the value from here to here. I got to subtract, right? And if I do the subtraction, R for Point Bernardino ends up being 30,359,368.465. I always like a check on that because I want to make sure I'm doing it right. So I know now my hypotenuse of the triangle. I know now my hypotenuse of the triangle. Questions so far? You guys are smart. Okay. What we have to calculate now is we've got to calculate gamma, or the convergence angle for where we are. And I'm going to try to show you what gamma represents and how we do it. I'm not a very good artist, as you've seen, but I'll try to do the best I can. Do I need to worry about that right now? Hang on just one second. Yep.
Isn't it theta?
No, theta is NAD 27. Theta was for NAD 27, gamma is for NAD 83. They changed all of the values so they wouldn't confuse the two. Mapping angle, convergence angle. Okay. Okay. Gamma, if you look at the formulas, equals L sub O, our longitude of the central meridian, minus, I'm going to call it L sub B, the longitude of Point Bernardino. There might be an L sub B. Yeah, there is an L sub B, so I'll call it BERN, so not to confuse it. The longitude of Bernardino times the sine of b sub 0. Per your formulas, the gamma equals the longitude of the central meridian minus the longitude of Bernardino times the sine of the sine actually of the central parallel, which is a constant for the zone, which is over here somewhere. So you could calculate this right now. Let me try to explain to you in my own way of how this works. Okay, here's the apex of the cone. And here's the center line of the cone, okay, which is also the center line of our datum, the ellipsoid. Follow what I'm saying so far? And if I draw here, and this represents the plane of the latitude of Point Bernardino. This represents, not very well, the plane of the latitude, if you will, through the latitude of Point Bernardino. So it's cut through the Earth at, wherever I put it, Bernardino, 34, 17, 42. And it's the plane of that parallel. Are we okay so far? Okay, before we go to there, you got to think about this in the terms of a horizontal curve, is the way I try to explain it. Okay? The length of a horizontal curve equals what? Weren't paying attention in construction, were you? Delta in radians times radius, right? Okay, the length in a horizontal curve equals delta radians times the radius. Okay, so far? If I draw from the intersection of the plane with the center line of the axis, I'm going to draw two lines out here. One, we're on that side. One represents L sub O. One represents L sub B. This is the difference of our longitudes, if you will. That's how we measure the difference in the longitude between L sub O and L sub B. The angle is measured here in the plane, if you will, of that latitude. Does that make any sense? Okay. Now, gamma, an angular value, is the angle measured between the same 2 points, but it's the angle measured at the apex of the cone. Remember, the convergence angle is measured at the apex of the cone. Okay, what's the approximate radius here of the in the plane? What's the approximate radius of the Earth? It's about 2906,000 feet, right? By the way, on the LS exam, well, you may not have that problem now because you're not doing it in writing. Used to be, on the LS exam, you had to be very careful to put your units on your values. You'd go through a whole problem like this, give them a northing and easting of a point and forget to put feet, get the whole problem wrong. So be careful of your values. I don't know if they're going to test you on that with the new testing they have, but be careful of your units of measure. It's a good way to lose all of your points. Okay, so the approximate radius here is about 2906. What's the approximate radius of this, if we look at this as the radius of a curve? It's going to be approximately something in this area, right? About 30 million feet, plus or minus a few 100,000, right? This is approximately R sub B. Everybody agree with that? So it's going to be plus or minus about 30 million feet. Think about this as horizontal curves. The length between this is the same. Whether you measure it, this is a horizontal curve, or think about this as a horizontal curve, the length stays the same, right? You guys look totally dazed. The radiuses will be different, correct? The radius is different. This radius is about 30 million. This radius is about 20 million. The length stays the same. What's going to happen to delta? Is it going to be exactly the same for both? No, it can't be because the radius changes. This delta will be less than this delta. Agreed? By how much? By that much. Sine of b sub o converts the difference in latitude and or difference in longitude between our point and the central meridian to the convergence angle gamma up here. It's about 57% less. That's where the sine of b sub 0. It's actually the sine of the central parallel of the zone. Okay? So what we have to do here is we take L sub O minus L for San Bernardino,